In this Python for Beginners course, we're going to be using ChatGPT, Claude, and Anaconda Assistant to help you learn programming faster. Because in 2024 and after, if you're not using AI tools to help you learn Python, you're wasting your time. Throughout this video, you're going to see the table of contents here on the left. So in Chapter 1, we're going to cover the basics of installation and getting started. Chapter 2 is going to be about variables and data types. Chapter 3 about if statements, so conditional statements. Chapter 4 is going to be about functions. Chapter 5 about loops. Chapter 6, keyboard shortcuts, because also they can help you save time. In Chapter 7, we're going to set up virtual environments. Chapter 8, first steps with NumPy. Chapter 9, first steps with Matplotlib. So with NumPy, we're going to do basic math operations, and with Matplotlib, we're going to create some graphics. In Chapter 10, I'm going to cover some frequently asked questions, because I've been giving Python courses for the past 4 years now, mainly to scientists and engineers. There are a couple of things that I see beginners struggle with over and over, and I'm going to cover that here because I want you to benefit from that experience and get around these beginner hurdles faster. Chapter 11 is just a glossary for your reference, and Chapter 12 is a summary of all the best practices that we cover in this video. You can download this Jupyter notebook either as a Jupyter notebook or as a PDF file from the video description, but I'm going to get there in a minute. Let's get started with the basics. By the end of Chapter 1, you'll be able to understand the concept of integrated development environments, know how to use AI tools, but also know their limitations because they aren't perfect, differentiate between Python scripts and Jupyter notebooks, write and execute a basic Hello World program, and understand the importance of code readability and the pip8 standard. Before we get to the installation and the actual programming, let's have a look why Python is the most popular programming language in 2024. So why should you be using Python instead of, for example, MATLAB, C++, or R? I've highlighted the main advantages in this table here. In terms of the learning curve, Python is the most beginner-friendly. In terms of performance, it is slower than C++, for example, because C++ is closer to machine level than Python is. However, you can optimize Python code by using NumPy, but also parallelization libraries that we're going to cover in the advanced courses. Meaning for most applications that aren't highly parallelized, high-performance computing simulations that run on supercomputers, Python is fast enough, or Python can be made fast enough. Use cases is another advantage of Python because there are so many external libraries that you can use to enhance the functionality of Python itself. So you can go into web development, data science, AI, and machine learning. In terms of data analysis and visualization, Python is definitely good at that, but I wouldn't consider that a massive advantage over the others because MATLAB and R are also pretty good at that. In terms of the cost, it's free and open source, contrary to MATLAB, which is pretty expensive. Language integration is also a great advantage of Python because if you do have C++ code or R code that you want to run out of Python, you can do that. So you can have your Python script or Jupyter notebook here and call a C++ program or an R program, let that run, and then read all the results from these scripts back into Python and work with the data there. In terms of machine learning and AI, it's also the leader in those fields right now, unless you want to do some very low-level machine learning and optimization that you would probably still do in C++, but all the high-level stuff you can better do in Python. In my advanced courses, I focus mainly on the science and engineering applications of Python because that is something I have a lot of experience with because I've been in the field for more than 10 years. However, if you do want to use Python for app and web development, there are some prominent examples here. So Netflix uses Python extensively, YouTube uses Python, Instagram uses the Django framework for its backend, and also the original BitTorrent client was written in Python. If you don't know what BitTorrent is, you're a better person than I am. Let's talk about IDEs. I've actually created 2 videos on this topic, comparing 13 different IDEs that you can currently use to develop Python code. In the first video, I boiled it down from 13 down to the last 3. And in the second video, I compared those 3 more in depth. Here, we're going to be using JupyterLab Desktop and Anaconda Cloud. But if you want to know why, watch these videos. In terms of the difference between JupyterLab Desktop and Anaconda Cloud, it's basically the same, just that JupyterLab Desktop you install on your machine locally, whereas Anaconda Cloud you can run in the browser, meaning you don't have to install anything, which can be beneficial if you're on a university computer or somewhere where you simply cannot install anything. The user interfaces of JupyterLab Desktop and Anaconda Cloud are very similar though, so if you use one at home and the other one at work or the other way around, you will not have to learn anything extra. In terms of the installation and setup of JupyterLab, I've already made a video on that, so I'm going to cut the most relevant parts from that video into this one, so you have everything in one video. We're going to look at some pitfalls to look out for when installing Anaconda and JupyterLab, and also which settings to set in JupyterLab to get the most out of it, and which functions to use in JupyterLab to get started. To download Anaconda, simply Google Anaconda download and you'll get to their download page. They'll ask you here to register, but you can skip that step and it'll take you directly to the download section where you have Windows, Mac OS, and Linux installers available. I'm on a Windows computer because most of the people that come to my Python courses are Windows users, so I want to show the problems that might arise in the Windows installation. I've also installed it on a MacBook and the issues were similar. The first couple of steps were straightforward. Now it asks you for a couple of customizations here. Start menu shortcuts you need. Add Anaconda 3 to my path variable. They don't recommend doing that. We can still do that later if we need it. Registering Anaconda 3 as the default Python 3.11. This is useful because when we install JupyterLab later, it will be able to use Anaconda, which is what we need. The next step might take a while, just took 5 minutes on this machine. In the last step, it asks you to launch Anaconda Navigator. It's not necessary. This is getting started. Let's have a look at that. It's just some documentation. You also don't need that. Next, let's install JupyterLab Desktop. Just Google it and you'll find the GitHub page. And from here, you just scroll down to the installation part. You have Windows, Mac OS, and Linux available. After downloading, you just install it. It's pretty straightforward. At the last step, it asks you to run JupyterLab. So let's do that. When you first start JupyterLab, this is what it looks like. On another computer, I had problems when starting a new session because there was no environment installed that it could run in. Let's see if we also run into that problem here. We actually don't. On this computer where everything is newly installed, everything worked out of the box. I'm going to cut in from the other computer what the problem looked like and what the solution was, just in case you run into the same problem. So you can start a new session here, which on this computer actually failed. Once you click on change the default Python environment, this window here pops up. It looks like this is the problem here. Let's install this bundled environment installation. With that, let's try again. New session. And with that, it finally worked. You might have to do another restart of the computer or of JupyterLab, but then it should work. You select the kernel, and now we can do our standard test just to see everything is working. A equals 5, B equals 3, print A plus B, and that works. I'm going to switch computers now because my MacBook is a lot faster than this Windows computer. We've switched to macOS. What you can do now, double click on a file to open it. This, by the way, also works in Windows. By default on macOS, it'll always go to the dark theme, at least for me. You can switch that here. When you go to the settings, theme, you go to the light scheme. The light theme looks better to me, but that is a matter of taste. Let's check out some other settings. You can go to the settings editor. Whenever you do anything in the settings that is different from the defaults, it'll show up here in the modified section. The most important thing you should change after installing it is to add these rulers. I usually add 2 lines, one at 80 characters and one at 100 characters, so you know when to do a line break. For some reason, JupyterLab has a couple of different places where to add the ruler. So one at the top, one here in the middle, and another one here. But the only thing you need to set is the one at the top. It might not show up immediately, then you simply need to restart JupyterLab. And then you have the lines that you can see here. Where you should do a line break is more or less regulated by the PEP8 standard. The PEP8 standard says you should do a line break after 78 characters, but also gives you some leeway to go up to 100. This is why I have 2 lines at 80 and 100. It depends on the size of your screen. If we switch to the second lecture, I can show you what I mean by that. You can, for example, have the lecture script open and the exercises, and if we pull them now to the side, you still want to be able to see both the lines in both scripts. Let's close our file explorer here, and then you can see both the 80 character line and the 100 character line in both scripts. However, this is a 32-inch monitor. On a laptop screen, depending on your zoom level, even 80 characters can be too much. Another thing that you can decide is how you want the UI to look like. So either multi-document IDE is what you see here, where you have these tabs. When you go to single document IDE, you only see the tab that is currently open and you have no way of switching, which for the settings means you basically cannot get out of the settings. To me, this is not very useful. So I usually stick to the multi-document IDE so you can use all the advantages that JupyterLab has, like switching between tabs. However, if you only want to work on one notebook and you want to go full screen and you don't want to have any distractions, I can also recommend the Zen mode, because here in the Zen mode, you have the entire screen for your script. Another thing I'd recommend using right from the start is the table of contents, so you can structure your notebooks by using these markdown cells. You see up here, this is not a code cell, but a markdown cell. When you use these hashtags, you can have multiple levels of headings. So with 1 hashtag, you get level 0, with 2 hashtags, level 1, and with 3 hashtags, you get level 2. By doing that, you get a nice structure in your notebook. First of all, when you scroll through it, it's a little bit easier to see what you are actually looking at. When you click here, you can also jump to the different sections. To get back to the launcher, you can always click this plus button here, or this plus button in the tab bar. To create a new notebook, simply click here. If we then run our standard test of A equals 5, B equals 3, print A plus B, run that, we see that works. We'll cover the pip 8 standard and more good programming practices in the advanced courses, so in Python Basics, Python for Scientists and Engineers, and Python for Biologists. If you go to my website, that's what it currently looks like, but it's going to get a design refresh soon. If you scroll down to the course overview, you see the 3 advanced courses here. If you scroll further down, you see the on-demand courses and the upcoming live courses. As I said, you can download the lecture script from this video in the description completely for free. If you want to get the exercises where you can take what you learned from this video and put it into practice, choose the Python beginner course using AI, where you can download the exercise sheet. For the first month after this video is uploaded, there's a 50% pre-sale discount because I'm still working on the exercises. They're going to be published in October 2024. Independent of that, if you leave a like and a comment and send me a message on LinkedIn, I'll give you an additional 50% discount. It'll help me grow the channel and it'll make it cheaper for you. For Anaconda Cloud, no installation is necessary, so you can just go to the website, create an account, and start coding. If you don't have an account yet, this is what it looks like. So it will say C sample notebook. After you've signed up, this will change. So here in Safari, I'm logged in, and it'll say launch notebook. When you click on launch notebook, this is what it should look like. So you can start new notebooks, start terminals, and I've created a folder here for the beginner course. So when you download the Jupyter file from the video description and upload it here to Anaconda Cloud, you can work with this notebook without having to install anything. In terms of AI tools, we're going to be using ChatGPT, Claude, and Anaconda Assistant. All of them have free versions, so you don't need to pay for them. And they're great at explaining code and concepts, so you can learn twice as fast. However, the code that AI tools generate isn't always working, or it's not always perfect, so we still need to learn programming ourselves. This is why we have this course. But AI tools can nevertheless help us a lot. In order to use Claude, go to claude.ai. This is what the website looks like if you don't have an account. So you create an account here, and after that, this is what it should look like. The only thing you need to configure is that you go to the settings, click on your email address, settings, and enable the artifacts. Why these artifacts are useful, I'm going to show you now. Go start a new chat. And just as an example, if you ask it now to compare Python to MATLAB, C++, and R, and give you that in a visually appealing table that I can copy paste into a Jupyter Notebook markdown cell, let's see what we get. You get the text answer on the left and the code on the right. This separation is called artifacts. And if you look at this table, this should look familiar, which is usually where I get the question, isn't using AI tools just lazy or isn't it cheating? There are only 2 types of people who will consider it cheating. So cars will look like cheating to people who sell horse carriages. So go with the times or get left behind. Or the second type of people are the dinosaurs who don't want to learn anything new. They just want to work with what they already know, with what they're familiar with what they're comfortable with. They don't want to leave their comfort zone. They don't want to learn anything new. But at the same time, they also don't want other people to use something new that might help them to overtake them. So no, I don't think using AI tools is cheating any more than using a calculator to do basic math is cheating. Because at some point also calculators were new, and before you had to do everything by hand. Calculators save time, and so do AI tools, so you can focus on the more relevant stuff. Because again, it's not like AI tools can do everything for you, so you just type one command and it writes the entire program that you need. You still have to think for yourself, you still need to learn programming yourself, and you still need to be able to fix errors that the AIs will make. If you want to dive a bit deeper into the limitations and abilities of the AI tools, watch these 3 videos, especially the first one. I put a lot of effort into it to use Claude and ChatGPT, so the tools we're going to use today, to build a snake game and an electron cloud simulation. While it did work in the end, it still needed some tweaking and some fixing along the way. So check that out. I spent a lot of time on that video. Something you should know as a beginner is the difference between Python scripts and Jupyter notebooks. To show you the difference, let's open a script. Here on the left, you have the file explorer. Let's make some space here and look at our snake game script. When you run a script, all the code will run top to bottom. There's no way of stopping somewhere in the middle, checking out some variables, and then continue running the code unless you use a debugger. Whereas in Jupyter, you have these code cells that you can run individually. You can put 1 line of code in a code cell, you can put 20 lines of code in a code cell, but you can execute it by itself. Let's say, for example, you read in some data, or you do some analysis in the beginning that takes 5 minutes. In the next line, after those 5 minutes, you have a bug. In a script, it will run the 5-minute part, and then it runs into the bug, the script crashes, and gives you an error message. Then you need to fix the bug, run the script again, and hope it doesn't run into another bug. Whereas with Jupyter Notebooks, you could run the part that is bug-free, so the 5-minute part first, and then afterwards, if in the next code cell you have a bug, you run it, there's a bug, you fix it, and you just have to re-execute that code cell. You don't have to run everything again, so you don't have to wait 5 minutes again. Another advantage of Jupyter Notebooks are the table of contents here on the left. This is something you cannot get in a Python script. So you can create these markdown cells, create your headings, create bullet points, and structure your code in this way and document your code this way a lot better than you can with Python scripts. So in Python scripts, all you can really do is add some comments here, and we're going to get to what comments are and how to use them later in the course, but that's about all you can do here. Whereas with these markdown cells, you can write entire texts here, add links, you can add pictures, you can add basically whatever you want. We'll also see later when we create graphics with Matplotlib that you can generate multiple plots and you can look at them all at the same time here in Jupyter. Scripts, however, are better when you want to run games like the snake game that I showed you. So you have one separate window where the game is running in, or you run a simulation with a video output like the Electron Cloud simulation. So Jupyter Notebooks have a lot of advantages, but also some pitfalls like the cell state that we're going to look at in chapter 2.3. The differences between scripts and notebooks are going to get more clear as we move along and code more throughout this video. For now, I just want to show you a simple hello world example. So if you want to run a classic print hello world, all you have to do here is write that down in a cell, hit Shift Enter to execute it, and you get the output. Whereas with a script, you have to create the script, hello-world.py, so this is a separate file. You need to create a terminal, and inside of that terminal, you need to write Python 3, and then the name of the script, hello-world.py. You get the output here inside of the terminal. Chapter 2, Variables and Data Types. By the end of this section, you'll be able to define and use variables in Python, identify and work with different data types, understand and use f-strings for string formatting, create and manipulate lists, tuples, and dictionaries, and know when to use which. Let's start with the different variables. By saying z equals hello world in quotation mark, you create a so-called string variable or text variable. So now the text hello world will be stored inside z. To create an integer, we can say x equals 16, which means the number 16 will be stored inside of x. For floating point numbers, you can do the same thing. So by saying u equals 1.3, the number 1.3 is stored inside of u. Python also natively supports complex numbers. So by saying complex number equals 5 plus 3j, the complex value 5 plus 3j is stored in our complex number variable. By the way, those variable names are names that I chose. You can choose different ones. It doesn't really matter what you call them as long as you remember what they were for. And the last type of variable is a special one. They're called Booleans. They can only be true or false, so on or off basically, and they're quite useful when we talk about if statements later. After we've defined all these variables, we can print them all. We see that z actually contains hello world, x contains the 16, u contains the 1.3, we have our complex number and also our Boolean. Now, if you get a variable and you're not sure what the type is, you can use the type command that will tell you, for example, for our complex number that the type is complex. I created an overview graphic where you can see it again. So Boolean can only be true or false. Integers are all numbers without a decimal point. Floating point numbers do have a decimal point, and complex numbers have an imaginary unit. And then we have strings for text. Let's have a closer look at strings, and with a little example, it should become clear why we need to use variables. If we're printing a little poem here, Tim is 4 and loves to play. He builds with blocks every day. 4-year-old Tim stacks them high. Tim's towers almost touch the sky. Execute that and we get exactly this text. What if we wanted to change the name and the age though? The name Tim appears 3 times in those 4 lines, and the age appears 2 times, meaning if we wanted to do it manually, we would have to do it now in 5 different places, and this is only 4 lines of text. Imagine you had a 200-page book and you wanted to change the names, then what do you do? Instead, what we can do is define the name and the age beforehand, and inside our string, we use f-strings, which means we have to put an f in front of the string. Then we can evaluate our variables inside of the string by saying name is age and loves to play. And by putting name and age in curly braces, we can execute this. And now everywhere where it said name, name is replaced by Max. And everywhere it said age, age is replaced by 7. Now Max is 7 and loves to play. He builds with blocks every day, so on and so forth. If you wanted to change something now, all we got to do is change the number here, execute it again, and our poem is updated. What's important here is that if you just change something here and don't run this cell, and you can see that by this bar turning orange, that if you now execute this cell, nothing changes. So you need to run this cell in order for the memory to update. If we execute it now, this turns blue again. And if we then execute this cell, our text is updated. We're going to be using f-strings quite a bit in the advanced courses because they're useful to, for example, create file names. So if you have a measurement of, let's say, a temperature, and you want to write the temperature value to the file name, you can do that using f-strings. Single and double quoted strings are the same, so it doesn't matter if you use 1 quotation mark or 2 quotation marks out here, so this will also work. However, if you have a text like Tim's towers almost touch the sky where you have an apostrophe inside of the string, if you then use single quoted strings, which is the same symbol as the apostrophe here, then we will get an error message because the print statement will think that the string ends here and it doesn't know what to do with all the rest. So if you do have apostrophes or single quoted strings inside of your string, use double quoted strings outside. Let's have a look at integer variables and some basic math. You can define a to be 5, for example, and print a. This works. One thing you can do in Jupyter is that you don't need to use print statements actually. You can just write out the variable name and that will print it too. However, this only works for one variable per cell. So if we put an a here now, then it will print out the a, not the b. So if you do want to print out multiple variables, use print statements. But if all you want to do is print out one, then you can leave out the print statement. We can do some basic math, c equals a plus b, and print c. That works. And don't worry, we're going to do more complicated math than this in the NumPy section, so in chapter 8 of this course. But for now, I just want to show you some basic math works out of the box. Let's talk about cell state. So one of the Jupyter Notebook pitfalls I talked about earlier, it's not really a pitfall, it's just something you need to be aware of. If you define x to be 5, y equals 2, and add those two numbers together, you get exactly what you expect. However, if later in the same Jupyter notebooks you use the same variable names again, so you define x to be 10 and y equals 15, for example, and then execute the cell again, you'll get 25 as an answer, because then it will use those two variables instead of those two. Which can lead to confusion, because if you only see these first two cells, you see x is 5 and y is 2, now y is x plus y 25, doesn't make sense. In a Python script, you don't have that problem because a Python script will always run from top to bottom. But in Jupyter, you can run cells out of order, which can be an advantage if you want to test things out. But in a case like this, be aware of it. It's not necessarily a bug, it's a feature, but it can lead to confusion. If you want to avoid this issue completely, simply never reuse variable names. Then it doesn't matter in which order you execute the cells, you will always get the right output. And one more thing to note here, even if I was to delete this cell now, this doesn't change anything about the output, because whether the cell is there or not doesn't really matter. What matters is that you executed it, and when you execute it, then x and y are being written to memory with these numbers, and they stay there until you either overwrite them or you restart the kernel. If something odd happens and you don't know exactly why, one thing you can always do is go to kernel, restart kernel, and run all cells. Your notebook should always work if you run everything top to bottom, because then it's basically running like a Python script, and this should always work. So if your Jupyter notebook doesn't run top to bottom, then you definitely need to fix that. You'll see me use comments like this one quite a bit throughout the notebook to clarify and explain things. And the way you can do that yourself is to start with a hashtag. And the comments can either be in a line by themselves, or you can add them at the end of a line. There are some best practices for comments. The first one being be clear and concise, so don't write entire novels, just get straight to the point, what it is that you're trying to do here. Update comments when the code changes, and yes, I've seen many examples of even experienced programmers not doing that. And then you're sitting in front of a comment that should in principle explain the code that's coming, but the code has nothing to do anymore with the comment that is there. It would be better to just delete the comment. So if you can't update it, at least delete it. Next one is avoid obvious comments. So don't state the obvious. If you do something like increment x by 1 in front of a line like this, anyone with a little bit of programming experience sees that this is what's happening here. However, what you do want to explain is why it's happening. So a good example would be to increment age after birthday. So when you add 1 to the age, you know why it's happening. So focus more on answering the why question rather than the what question. One thing comments are used for in Python scripts is code sectioning. For example, this part is about data processing, then about model training, and then some result analysis. However, in Jupyter Notebook, you have markdown cells for that with headings, which has the added benefit that you have the table of contents here on the left, and you can click it and jump right to the section. The last one is to-do comments. So if you implement something quick and dirty and you want to remind yourself that you need to implement something else later, so for example, implement error handling for invalid inputs, this is something you can use to-do comments for. And if you then search for to do in your notebook or in your Python script, then you find all the right places where you still have work to do. Last comment here, while comments are important, it's even more important to give your variables and functions proper names. So instead of calling your variables A1, A2, B3, B4, call them what they are. If it's an energy, call it an energy. If it's a temperature, call it a temperature. If it's a distance, call it a distance. And the same with functions, the function name should already answer what the function is doing. The more you do that, the less you need to rely on comments. Next, let's have a look at data structures, namely tuples, lists, and dictionaries, where you can save multiple variables in one data structure so you can keep values that belong together in one data structure. Let's start with tuples. Tuples cannot be changed after creation, so they are constants. You can create them by using round brackets. For example, for coordinates, you could say coordinates equals, and then in round brackets, 5 and 2. The 5 and 2 will be stored in the coordinates tuple, and they will stay together. However, if you now try to change something about that, this will not work. So this will give an error message saying tuple object does not support item assignment. So again, tuples are constants. Tuples are used by functions, so if a function has more than one return value, tuples are used. Next, let's look at lists that are a bit more flexible than tuples. So instead of doing something like temp1 equals 5, temp2 equals 7, temp3 equals 10, you can create a list using square brackets. So instead of round brackets for tuples, you use square brackets for lists. And when you print that, you have all your values in one list, meaning you don't have to come up with a bunch of variable names. Once you have created a list, you can also append to it by saying temp, so the list name, dot append, and then another value. You can add this value to the end of the list. With lists, mixing of data types is possible. I don't know too many examples of where that would be useful, but it is possible. So if we define our list to be 1, x, 4, 6, 8, x being a string here, then we can do that. If we want to access the individual list elements now, we can write out the list name and in square bracket the index that we want to have. So when we print that, test list 1 of 1, we get x, which might be confusing because x is in the second position. So why is a 1 giving us the x? It's because in Python, like in C, we start counting at 0. So the 1 here would be index 0, the x is index 1, the 4 is index 2, 3, and the 8 is index 4. Keep that in mind. This is something I saw beginners struggle with to wrap their head around the counting in Python. If we want to have multiple elements from our list, we can write the list name, so test list 1, from 0 to 2. And this will give us the first element, the second element, so the 1 and the x, but not the one with index 2. Meaning the way to read this is go from 0 up until 2, but not including 2. This is the same for NumPy arrays that we're going to look at later. It uses the same indexing logic. Again, just get used to it. It's not too intuitive from my perspective, but you just need to wrap your head around it once, and then you can always use it like this. I think the reason why they exclude the 2 in this example here is because if you say I want the test list from 0 to 2 and the test list from 2 until the end, you get the entire array back. You can use the same index in both cases here and you get the entire array. From 0 to 2 gives you 1 and x, and from 2 until the end gives you 4, 6, and 8. By not putting any index here, it means go until the end. If you have two lists and you want to put them together, use the plus operator here. When we define a second list, test list 2, again with mixed data types, we can say test list 1 plus test list 2, save that in the merged list, and then we have all the entries from both lists in one. If you want to remove elements from a list, you can either do it by value, so by saying merge list.remove of x, that removes the x, so from here to here, the x is gone. Or you remove by index, where you say merged list.pop of 1, and this will remove the item with index 1. So from here to here, the 4 is gone. One more thing is sorting. If you have a list of strings, you can sort them alphabetically with the .sort command. And if it's a list with numerical values, it will sort them numerically. So when we print that, we get B, C, C, H, P. So sorted. In the advanced courses, we'll mainly be using NumPy arrays, pandas data frames, and dictionaries. So I'm going to keep this section about lists relatively short. However, if you do want to know more about lists, you could go to Claude now and ask it to tell me about Python lists and everything I can do with them. And to give you that example, let's do that now, see what we get. So we can paste our question in here. Let's see what happens. So we got our answer. Claude will tell you Python lists are versatile data structures that can store a collection of items. Here's an overview of what you can do with them. Creating them, accessing elements, so basically what we just did. Also with slicing. More common list methods, so append we looked at, extend, insert, remove and pop we talked about, clear, index, count, sort, reverse. You can do list comprehensions, which is very Pythonic. However, I always find this to be less readable than just writing it out like you normally would. If you look online for documentation, sometimes you will find this in some Stack Overflow forums. So people will do this. If you wanted to know more about list comprehension now, you can ask Claude about it. But personally, I don't like using list comprehension in my code because I think it just makes it less readable. Now we have list operations. So the concatenation we already talked about, repetition. Some more built-in functions, length, max, min, sum. But again, this is stuff that you would normally do in NumPy, so I wouldn't bother learning about this. Membership testing, so you can check if a number is in the list, but maybe wait until we've actually talked about if statements. iterating over lists so you can loop over them. This we're actually going to cover in the loop section of the course. And 10 multi-dimensional lists. So you can have lists in multiple dimensions, but again, this is more something I would do with NumPy rather than with lists. If you want to know more, you could ask Claude now to provide more examples or to elaborate on any of these points. For example, list comprehension might be useful to at least know about it. So you could ask, please tell me more about list comprehension. And that will give you an explanation here. And if you have any questions about any of this, you can always ask Claude more and to elaborate more. But possibly wait until you watch the entire video so you know what if statements are, what loops are, and also what NumPy arrays are. Then dive deeper into the details. Let's go back. Let's look at dictionaries next. They're used quite a bit in Python, both by beginners and also by advanced programmers. So they're definitely used in the advanced courses. The idea is like a classic dictionary where you can look up the word car, for example, and you get a definition. Here in Python, car would be the key and the definition of car would be the value. Every key only appears once in the dictionary. Let's have a look at how we define them and access them. For dictionaries, we use curly brackets. Remember, tuples were round brackets, lists were square brackets, and dictionaries are curly brackets. How do we define dictionaries and how do we access them? Contrary to lists where you have indices, so 0, 1, 2, 3 for all your array elements, here you have key value pairs. The key is always a string on the left. So for the first element, it's name and the value is Alice. Next key is age and the value is 30. Next key is phone and the value is a generic phone number. If we want to access these elements now, we're not handling indices, but the keys. When we print person of name, that gives us back Alice. When we print person of age, that gives us 30. Alternatively, instead of accessing it directly, you can use this getter function. So person.get and then phone, which will give you back the phone number. The advantage is if you here change something, so you have a typo, it will give you none back. So you will not get anything back. Whereas if you make a mistake here, you'll get an error message. So better to use the getter function just to be on the safe side. Now I created a graphic here to explain the differences between dictionaries and lists. The main difference being that lists have indices and dictionaries have keys. In principle, you can save the same type of data in there, but instead of having to remember that 0 was the name, 1 was the age, 2 was the phone number, here you can give it names that actually mean something to you that you will remember. You can access them with name, age, and phone. We will be using dictionaries again in the Matplotlib section of this video, so chapter 9. And just in case my explanation wasn't clear, you could ask Claude what are the main differences between lists, tuples, and dictionaries in Python. The answer was actually so good that I copy-pasted it in here, why we use dictionaries, and compare them to the other data structures. The difference to lists and tuples we talked about. NumPy arrays are mainly for numerical data, and we're going to get there in chapter 8. And pandas data frames we're not going to talk about, but we will be using them in the advanced courses. Pandas data frames are, for example, useful if you have Excel type data and you want to process that in Python. So for everything data science related, pandas data frames is what you would use. Chapter 3, if statements. By the end of this section, you'll be able to write basic conditional statements using if, elif, and else. Use comparison operators like is equal to, is not equal to, smaller, greater than. Combine conditions using logical operators, so and, or, and not, and understand and apply Boolean logic in a programming context. So what are if statements? If statements are something we encounter in everyday life also. Like our friend here, if I'm hungry, I'll go eat. That's a conditional statement. Only if he's hungry, then he's gonna go eat. If I'm sleepy, I'm gonna go to bed. If it's raining outside, I'm gonna take an umbrella. And in programming, you can use if statements to control the program flow. If some condition is true, then you do one thing, and if it's not true, you do another. Same as in real life. To understand if statements, we have to understand indentation first. If we do something like this here, I equals 0, and then say if I is equal to 0, notice the difference here, I equals 0 assigns 0 to I, and with equal equal, you check whether these two things are actually equal. So if I is equal to 0, then we print I is 0, else we print it is not 0. What's important here syntax-wise is that you do need the colon here and you do need the indentation here. So if we run it like this, everything will work. Should you forget something, should you not have the colon, you'll get an error message, which is actually kind of nice because it tells you it expects the colon. Also, should you not use indentation here, that will also give you an error message. So indentation is how Python indicates blocks of code that belong together. What you can do after an if statement is not limited to one line, but you can have additional lines of code here that are also only applied if I is equal to 0. Arbitrary use of indentation creates an error. While f equals 1, this will work without problems. However, if you did something like this, g equals 1 with a bunch of white spaces in front, you'll get an unexpected indent error. You would either have to delete that all or just comment it out again. Another way how you can use if statements is with Boolean variables. So you can define them beforehand. For example, is it sunny? It's false, so it's not sunny. And then we ask if is sunny. So if our Boolean variable here is true, then we say enjoy the sunny day. Else, so when it's not sunny, don't forget your umbrella. When we run that, because it's false, we say don't forget your umbrella. And when we set it to true, we enjoy the sunny day. Notice how this is not any different from what we did up here, because I equals 0 will also either be true or false, just that we do it here directly inside the if statement. If you had multiple conditions now that you want to check for, to stay with our weather example, let's say it is sunny, but it is not warm, and you want to check for both. You could say if it is sunny and it is warm, enjoy the warm sunny day, take sunglasses, else it is either not sunny or not warm or neither. So in order for us to understand this, we need to understand that this statement here will only be true, so we only get here, if both of these are true. Meaning, if one or both of them are not true, we automatically land in the else block. So down here we don't really know, is it now not sunny or not warm or neither? The only thing we know for sure is if we land up here, then both of them were true. Let's try that out. So if we set both to true, we enjoy the warm sunny day. However, if even one of them is false, we land in the else block. It doesn't matter which one. The or operator, on the other hand, checks for whether at least one of them is true. If we say if it is sunny or it is warm, it's enough if one of them is true, and again, it doesn't matter which one, but they could also both be true. Then we say it is either sunny or warm or both, because here we don't really know. Is it sunny? Is it warm? Because one of them being true is enough to end up here. Here's the other way around than what we had for the AND statement. Only in the else block we know exactly which combination we have, because in order to land down here, we know it is neither sunny nor warm, because only then will the or statement be false. If one of them is true, true, false, we execute that. We land up here. If we switch that now, let's say this one is false and this one is true, we also land up here. If both of them are true, we also land up here. And only if both of them are false, we land down here. To understand this concept a little better, I created two tables here and some graphic. So we have 4 different weather conditions, right? So it could be either sunny and warm, it could be sunny but not warm, it could not be sunny but warm, and it could neither be sunny nor warm. So we have 4 cases to check for. Our logical operator AND will only be true if both of them are true. So only for case 1 will AND be true. And our OR operator will be true for cases 1 to 3, so as long as at least one of them is true. However, in case 4, when both of them are false, then the OR operator will go to the else statement. What could we do if we wanted to catch all 4 cases and be 100% sure that if we end up in a certain if or else block, then we know it's either case 1, 2, 3, or 4? For that, we can use the Elif statement. In the beginning, we can ask the same thing that we asked for our AND example. So if it is sunny and it is warm, so we're basically asking for case 1. We say, enjoy the warm sunny day, take sunglasses. Instead of jumping right to else, we can say Elif, which is basically else if. We know this wasn't true. The next thing we check for is Elif, is it sunny and not warm? This is our case 2 up here, sunny and cold. Then we can print, it is sunny, but it isn't warm, take a jacket. To check for case 3, again, we can use an Elif, so we know those 2 weren't true, meaning it wasn't case 1 or case 2, so it could be either case 3 or 4 at this point. And since both for case 3 and 4 we already know it's not going to be sunny, we don't need to check for is sunny again. All we need to check here is whether it's warm or not. And the reason for that is if we end up down here, we already know that it wasn't these 2. Because if it was, Python would simply jump in here or here, do the print statement, and then it jumps out of this entire block. So Python doesn't check for all the different conditions that you set here if one of them was already true. The fact that we end up down here means it wasn't 1 or 2. To differentiate now between 3 and 4, all we got to do is to check whether it's warm or not. So we say Elif is warm. That would be case 3. It's not sunny, but it's warm. That is exactly what we print here. Take an umbrella. For else, we don't need to check anything anymore because we already know it wasn't case 1, 2, or 3. So case 4 is the only one left. Then we can just say it is neither sunny nor warm. just stay home, why bother? Why bother going outside? So in case this wasn't exactly clear, so it's not clear why we didn't have to check for not sunny in case 3 and 4, you can copy the entire cell, paste it to Claude, and then ask it what it was all about. So when we start a new chat, we can copy paste this entire code cell in here, hit Shift Return for a new line, so it has access to the entire code. And when you do that, make sure that the code that you're pasting in here actually contains all the variables and all the functions and all the libraries that are used in that cell. Because otherwise, Claude only has half the information and then it usually can't give you a proper answer. We can ask it, explain this code cell to me. How do these if statements work? Why did we not have to check again for is sunny in case 3? When we get our answer, the first point is that we set our Boolean variables. Scroll down so we see the rest. It explains the if, elif, else statements here. But the most important thing is point 3. The if statements work by evaluating the conditions in order. As soon as a condition is found to be true, its corresponding code block is executed and the rest of the conditions are skipped. Regarding the question about case 3, we don't need to check is sunny again because of the order and logic of the previous checks. The reason I'm hammering on this is so you understand not just how if statements work, but also how you can use them in a smart way so that you don't repeat checks unnecessarily. Next thing, creating Booleans by comparison. When you say something like 1 larger than 0, that will return a Boolean variable. This will either be true or false. So 1 larger than 0, obviously it's true. 1 smaller than 0 is false. 1 equal to 0, also false. Let's get back to our original example. We can set I to 5 and check for whether it's equal to 0, smaller than 0, or else. We don't need to check whether it's larger than 0, because once we get to the else statement, we already know it's not equal to 0, it's not smaller than 0, so it must be greater than 0. This might have been quite a bit of theory in this section. However, if you do understand now what Boolean variables are, how conditional statements work, so if, elif, and else, how to use the logical operators and, or, and not, how the comparison operators work, that's all the foundational knowledge you need for the advanced courses, and it's about 80 to 90% of the knowledge you'll ever need when it comes to if statements in Python. Chapter 4. Functions. By the end of this section, you'll be able to define and explain the purpose of functions in Python, create functions with the def keyword, understand the concept of parameters and return values, call the functions and use the return values, explain the differences between local and global scope, and apply some best practices in function naming and usage. The simplest example is a hello world function, so we use the def keyword to define a function. By using def, Python knows a function is coming. You give it a name. In parentheses, you put the input arguments, which in this case we don't have any, but we'll get there. Similar to the if statements, at the end of the line you have a colon, and then need 4 spaces or 1 tab as indentation to print hello world. Also here, you could add a lot more code here that would all be part of the function. However, what you will notice when you execute the cell, nothing happens. Doesn't matter how many times you execute it, nothing happens. So where's our hello world? We actually need to call the function for the function to be executed. If you just define a function, it's just a collection of code that is just waiting to be called. But in and of itself, just defining a function doesn't do anything. If we call it in the next cell, that's when we get our hello world. We can call it however many times we want, we always get the same result from our function. The concept of functions is that you have input arguments, you put them into the function, then some kind of processing happens, and then you have an output of that function. A simple example of that is our square function here. This time we do have an input argument, x, and we return x squared. If we then call the square function with the argument 3, we get 9 as a return value. The value 3 is given as an input argument to our square function. It's being squared and returned. If we don't just want to print our return value, but actually save it for later, we can save it in a variable, then we can print that variable later or do additional processing with it. For example, use this output from one function as an input for another function. One function can have multiple input values. It's not limited to just one value. Here we have a multiple input function with x and y. We return x squared plus y squared. Call it with 2 and 3 as input arguments. So x is 2, y is 3, x squared is 4, y squared is 9, 4 plus 9 is 13. If this wasn't clear, feel free to ask ChatGPT or Claude to explain the concept of return values and functions in Python and why they're important. Which brings us to the question, why use functions at all? One is to organize code. You can have a collection of functions that you can use not just in your notebook here, but you could also use them in other notebooks and Python scripts so they make your code more portable. You avoid repetition, so if you want to do the same math operation on an entire set of data, you don't have to copy paste that command over and over again, you can just call the function. You enhance readability because you can name your functions in a meaningful way and then you know exactly what's happening. And it also improves maintainability. So let's say you call a function in 10 different places and then you want to change something about the formula or you want to change what the function does. If you had copy pasted that part of code in 10 different places, you would have to go to all of these places individually and change the code now. Whereas a function, you can change it in one place, rerun all the code, and all the 10 function calls are updated automatically because the function itself is updated. This might seem like dry theory, so let's look at an example. If we measure some kind of temperature and we say it's 30 degrees, then we want to calculate some other quantity from that. So we say that our temperature squared plus temperature plus 5, and then we can print that result. The result for 30 is 935. Let's say we want to do that for one more, or maybe an entire data set of numbers. What would we have to do without functions? We copy paste that entire cell and change the temperature now. We have temperature 2 is 40 degrees, result 2 is temp2 square plus temp2 plus 5. Then our result for 40 is 1645. However, if we put this calculation into a function, we can say definition of polynomial function of x is x squared plus x plus 5, which by the way is already easier to read than what we had here. Now that our function is defined, we can call it with different temperatures, as many as we want, and this is a lot more readable than all of this. If we wanted to do this now for, let's say, 100 different values, we would have to copy paste this 100 times, whereas this function will always say 2 lines of code, and all we gotta do is call it for 100 different values. Which, by the way, later when we use NumPy arrays, we don't have to do it one by one, but we can plug our entire array into that function. But we're gonna get there in chapter 8. Similarly to how a function can have multiple input values, a function can also have multiple return values. As an example, we can calculate the min, the max, and the average of a list of numbers. For the minimum, we use the min function. For the maximum, we use the max function. For average, we use the sum function. Those are built-in functions. Whenever your code turns green, that is something that is already built in to Python. So never give your own variables or functions names that are already reserved by Python, because that could lead in best case just to some confusion. Worst case, you get weird results. The average here is the sum divided by the length of the number. When we return it, we can return the minimum, the maximum, and the average. Define that function, define our list of numbers, call our min-max average function. We'll see that 1 is the minimum, that's here, 9 is the maximum, that is here, and this is the average. Remember when I said in chapter 2.5 that functions use tuples as return values if you return more than one number? Here you can see it. This is a tuple. If you want to get those values out of the tuple, you can define minval, comma, maxval, comma, averageval equals and the function call that will save it into these 3 different variables that you can then use individually. Keep in mind that you can use the built-in functions in Python like min, max, and sum. However, for all the mathematical stuff, we'll be using NumPy in the advanced courses that we introduced in section 8. Also, a lot of built-in NumPy functions have multiple return values, and also they will return a tuple. So the same that you learned here will also apply there. One thing that in my opinion is not taught enough in beginner courses in Python is scope. Let's have a look at what it is and how it can help you. Variable scope basically means where you can access it. You can have global variables and local variables. All the variables that you define inside of a function are local variables and they cannot be accessed outside the function. The best way I think I can explain this to you is with this picture here. Let's say you have a code x equals 16. You define a function where you set x to 64 and print x. You call my function and print x. My function will give you an output 64 because that's what x is inside of the function, but that will not actually change anything about the global x variable. When you then print x, x is still 16. So this x and this x are 2 different variables. Ideally, you want to keep the scope as small as possible, so use functions as much as you can, and also inside of functions use local variables instead of trying to access global variables. It's possible, but it's not good programming practice, because if you took this function now into a different code, so into a different project, and it's dependent on some global variable, then you can't really port it, because then you would also have to port that global variable and everything else that comes with it, and then you have a whole bunch of dependencies that you simply don't want. If all the variables that a function works with are either input arguments or local variables, then you can take that function anywhere. Why am I hammering on this? Why is this important to me, or why should it be hopefully also important to you? First of all, you can prevent naming conflicts. So if you reuse a bunch of variable names, then inside of the function that doesn't matter, because if you define a bunch of functions and they all name their variables x, y, and z, that doesn't matter because they can't access each other's variables anyways. If a function only uses the local variables and the input arguments, that improves also the code organization, so you can read it easier than if it accesses some global variable that might be defined elsewhere that you don't see in that moment. So only using local variables also helps you understand your own code and other people's code easier. And it also enhances debugging. So if you have a bug and everything that's being accessed is right in front of you, it's easier to see the problem than if you have one function that accesses 10 different global variables, changes them all, and then you get a bug and you don't know where it's from. Let's look at an example. We define a global variable, say I'm global. Inside our scope example function, we define a local variable, I'm local, print our global variable inside the function, local variable inside the function, call our function and print our global variable. This works, so this is from inside the function, this is from outside. However, if we now try to print the local variable, so the variable that we defined and output it here, we get an error because out here this local variable is not defined. An example of only using local variables inside of a function is this here. So instead of doing this, global data equals 10, then you say process data without input arguments, access global data, then you return global data times 2. Then you have something called side effects, so inside of the function, some global state is being modified. Instead, prefer to do this. So you process your data, you have some input data, and then you return the input data times 2. This makes it more readable, side effect free, and also easier to debug. Let's finish off the chapter by looking at error messages. We had our polynomial function earlier. If we try to call that polynomial function now with a list, then that wouldn't work. It will tell us unsupported operand type, list and integer. So this we cannot do. We can do that later with NumPy arrays, but here what I want you to learn is how to deal with error messages, because you will be getting them. Everyone gets them, so it doesn't matter if you're beginner, advanced, or expert programmer. We all run into error messages, so it's not about not making mistakes, but knowing how to handle them. Ideally, with a little bit of experience, you see an error message like this and you know immediately what the problem is, so you know you cannot call a function with a list. However, as a beginner, you don't have that experience, so you don't know necessarily what is wrong here. So what do? This is a good example of something AI tools can help us with. So we can either copy-paste that code again into Claude or ChatGPT like we did before, or we can use Anaconda Cloud because the built-in Anaconda assistant can read your code on the fly. So you don't need to copy-paste anything, you can just read what you're doing. Let's try that out. This is the same notebook in Anaconda Cloud. If we run this here, as long as it's commented out, we don't get an error message. But as soon as we do get an error message, Anaconda Assistant actually pops up here. We can debug the active code cell. This was actually not what I wanted to show you. This was actually not the error message that I wanted to show you, but Anaconda Assistant is of course right if it says the error occurs because the function polynomial function has not been defined before you try to call it. Of course, because here it's only in a comment. And the reason I put it in a comment here is because we already defined it higher up in the notebook, and you don't want to define the same function over and over again. You only want to define it once and then leave it be. Because otherwise, when you try to change something about the function, you would again have to change it in 3 different places, which kind of defeats the purpose of having the function in the first place. Here we can create a quick copy just so we have everything in one place. So we can copy this cell, delete the comments here, and make it a code cell, clean up a bit. Now it's a code cell. If we run this again, we get a different error message. Let's try to debug that one. I think the message here will not be too useful because it doesn't know about the polynomial function. It can only debug things cell by cell. So unless the function and the call of the function is in the same cell, Anaconda Cloud doesn't have all the information. But let's have a look. It says the error occurs because the code is trying to perform an exponentiation operation on a list instead of an individual element of the list. To fix this, you need to ensure that the polynomial function processes each element of the list individually, rather than trying to apply the operation to the entire list at once. Would you like me to provide the correct code? This actually worked without it even exactly knowing about the function. So let's see what it gives us if we ask it for the corrected code. Here is where you need to be a bit careful with these AI tools. So it gives you some code and this will work. However, it redefined a polynomial function to be something else than what it was before, because it did not read the polynomial function before. If we wanted a better message, we can merge these 2 cells now so that it knows about the polynomial function. So when we ask it to debug this cell, it will know everything that it needs to know. We can start a new conversation, debug the active cell. We get more or less the same error message, but now let's try to ask it for the corrected code. Now the corrected code that we get actually solves the problem with our definition of the polynomial function by calling it one by one for every array element using a loop. And we're going to get to loops in chapter 5, so the next one. To sum it up, Anaconda Assistant cannot read your entire code, understand it, and then give you suggestions. You will have to put code that you wanted to understand into the same cell for it to give you proper recommendations. Which begs the question, why not put everything into one cell to begin with, because then Anaconda Assistant can just read everything. For Anaconda Assistant, that would be best. But for you to run code line by line, cell by cell, you do want to split up your code into different sections to run and execute and debug them independently of one another. By the way, how to merge them, how to do all that stuff, we're going to cover in the keyboard shortcut section, chapter 6. To become better at error handling yourself, I created a list here of all the different errors that you might get. There are syntax errors when, for example, you print hello world without the parentheses. That will give you a syntax error. Indentation error we already talked about. So if you have an if statement and then don't indent, that will give you an indentation error. There are name errors when you try to print or access some variable that you haven't defined before. That will give you a name error. There are type errors if you want to add two variables together that are not of the same type. Here a string and an integer. That will not work. So you either have to convert the string to an integer by casting, like so, or you have to convert the integer to a string with a string casting, depending on what it is that you want to do. There are index errors when you try to access an index that isn't part of a list. Here you have my list 1, 2, 3. You have the indices 0, 1, and 2. If you then try to print my list of 3, that will give you an index error. Lastly, there are key errors that we already saw in the dictionary section. If you have a dictionary and you try to access a key that isn't there, that will give you an error message. So, what to do when you encounter an error? First of all, read the end of the error message carefully. Often the important stuff is at the end. You saw that, for example, when we try to call the polynomial function on our list, the type error and all the relevant stuff here, and everything that comes above is just pointing you at which exact line it happened. Which brings us to point 2. When you get an error, check the line number and the surrounding code for issues. If you're unsure, try searching for that error message or use the AI tools for help. And remember, everyone gets error messages. Doesn't mean you're stupid, doesn't mean you're not talented, doesn't mean you're not cut out for this. It's just part of the process. Chapter 5. Loops. By the end of this section, you'll be able to understand the concept of iteration in programming, write and use while loops, implement for loops to iterate over sequences, and to avoid and handle infinite loops. Let's start with while loops. If you define I to be 0, you can say while I is smaller than 6, as long as this condition is true, same as for our if statements earlier, this block of code is executed. With a difference to an if statement is that at the end of this block of code, we jump back to the statement. If it is still true, we execute this block of code again. So what happens here? We set I to 0, and we say while I is smaller than 6, which 0 is smaller than 6, so this is true. We print I, so we print 0. Then we set I to I plus 1, so now I is 1, and we go back to the statement. Is I still smaller than 6? 1 is smaller than 6, that's still true. So we print I again, so now we print 1. Then we set I to 2, and this will carry on until I is 6. And then this statement here, 6 smaller than 6 is not true, it's false. And only then do we exit this while loop and print have fun. So let's have a look at the output. First loop iteration, we get the 0, then the 1, then the 2, 3, 4, 5. So when I is 5, this statement reads, is 5 smaller than 6? Yes, so we print the 5. Set I to 6, and then 6 is not smaller than 6, so we exit the while block and print have fun. With while loops, you need to be careful to define your criteria here, because if this is a criterion that will never be false, then the loop will run indefinitely and will never end, and this can crash your computer in the worst case. To give you an example here, if you have a while true loop, print this is an infinite loop that will never end. When we execute that, luckily, Python or Jupyter catch this error, so it doesn't let you print all these statements. But when you have executed an infinite loop, what you can do is hit escape, hit II to interrupt the kernel. It's the same as going here to kernel interrupt. That will stop any running cell. So after that, you generally want to restart the kernel and run up to selected cell or run all cells. But before you do that, you definitely want to comment that out again. Then we can run everything up to the selected cell, restart everything, and you can fix your error. Now the error is gone, and we can have a look at for loops. For loops are a little different in the way that we define the loop criterion. When we say for letter in hello world, print letter, then print have fun, what do we get? We get each and every letter or character of the string individually. So you can think of a string as a list of characters. Note here, because this is a question I get quite often in my courses, does it matter that we call it letter? Does Python understand the word letter or character? You can answer the question by looking at what Python marks green. For is something built in is something built in. The print function is something that is built in that Python understands, but whether we call it letter or a doesn't matter. Yeah. This loop statement knows you want to take this string and loop through it one by one. And at every loop iteration in a for loop, one character is being stored in a. And inside the loop body, everything that's indented here is called the loop body. You can then either print it or do something else with it. And the same works for list. When we define a list of binary numbers, we can run that. Binaries is this entire list. For the first loop iteration, the number 2 will be stored in number. Then we go into this print statement. We say I am at number now, so I am at 2 now, using the f strings that we looked at earlier. In the next loop iteration, the number will be 4. We print I am at 4 now, and so on and so forth until we reach the end of the list. You could ask the AIs now, explain the difference between a for loop and a while loop in Python. When would you use one over the other? And I tried to visualize the answer to this question. In a while loop, you enter the loop, you have some kind of test expression, while I is smaller than 6. And if that is true, we go to the statements or the loop body and execute those statements. After they're executed, we test the expression again. So is I still smaller than 6? If true, we continue in this loop here. Once it becomes false, we exit the while loop. Whereas for loop, we will always say for each item in sequence. When you already have a list or a dictionary or a string or a NumPy array, and you want to do something for each and every element in that sequence. The only question that is asked here is, have we already reached the last item? If not, we go to the statements until we reach the last item. Once that becomes true, we exit the for loop. Should that not be clear, go to the AI tools and copy paste this question. It can explain that concept further. What I want to show you here, because I haven't shown it in the script, how we can iterate over a dictionary. Copy paste that question. We get our answer with a nice code example. We have a sample dictionary of fruits, apple 3, banana 2, orange 5, and loop over it with a for loop. For fruit, comma, quantity, so that we get both the key and the value in fruits.items. So fruit.items returns the individual key value pairs. So at first it will be apple 3, the second loop iteration will be banana 2, third iteration will be orange 5. Then we can say we have quantity fruits. When you run that, you get we have 3 apples, we have 2 bananas, and we have 5 oranges. Claude will also explain the code. In this example, fruits.items returns a view on the dictionary's key value pairs. The for loop unpacks each pair into fruit, the key, and quantity, the value. So similar to what we did with the tuples. Then it asks you if you want to explain it further. If, for example, it's not clear how we can extract 2 values at the same time, you could ask that question now, and Claude would explain further. Chapter 6, keyboard shortcuts. First of all, the shortcuts that I show here for JupyterLab also work in VS Code. So they're not JupyterLab specific. To get into command mode, hit escape. All the other commands that I show here require you to be in command mode. If you are in edit mode, so if you're in here, either just hit Control Enter to execute a cell or hit escape to get out. If you see this blue bar here on the left, that means you're in command mode. We've already talked about how to interrupt the kernel. In command mode, hit II. If you want to create another cell, and if you want to create the cell above, hit A, so A for above, and B for below. You can convert a cell to markdown. By default, everything's a code cell, but if you hit M while in command mode, this will be a markdown cell. So if you write something here now, that will be a markdown cell. If you want to turn it back into a code cell, hit Y. If you execute it now, you will get an error message because that isn't code. Hit DD to delete the cell. By now, you've probably seen me do this a bunch of times. If you create a cell and you hit Shift Enter, that executes the cell and marks the one below. If you want to stay inside the cell, you can hit Control Enter. So then you can hit it multiple times. To move around your notebook, you can use the arrow keys. So if you hit arrow up, this will go up, arrow down will go down. To mark multiple cells, you can hit Shift up. Let's create a couple more cells here so that it makes sense. If you wanted to delete them all, for example, you could mark the first one, hit Shift, and then arrow down and hit DD. Then all of them are deleted. Let's create a couple of cells here. If you wanted to copy that to the end, hit C, move wherever I want to have it, and hit V. If you don't want to keep the original cell, so cut and paste, you can hit X. That will cut the cell. And again, small v for inserting below. To comment and uncomment some code, Let's say you have some garbage code here, and while you're in edit mode, so while you're in the cell, hit Control/ on Windows or Command/ on macOS. That will comment it out. If you hit Command/ again or Control/, it will uncomment it again. If you want to undo something that you did, so let's say you had something important here and you wrote some other code and you deleted this and you want to go back because maybe you deleted something that you didn't want to delete, you can hit Control/Z on Windows or Command/Z on Mac and it's back. If you realize, oh, that was actually fine having it deleted, you can hit Control-Shift-Z or Command-Shift-Z. That will redo the changes. There are many more shortcuts, but I've made the experience that if I show people too many shortcuts, they're going to end up not using any of them. So the most important thing I want you to take away from today is to at least use Shift-Enter or Control-Enter in order to execute a cell. What I do not want to see in my courses, if you come to the tutorials and you want to show me some code, is that you mark a cell, write some code, and go up here and run the selected cell. This way you're wasting everybody's time, your own, mine, and everybody else in the tutorial. It's simply not necessary. Go to the cell, hit Shift-Enter, and you're done. Chapter 7, Virtual Environments. By the end of this section, you'll be able to explain the purpose and benefits of virtual environments in Python, create and activate virtual environments using conda, install and manage libraries within an environment, understand the difference between conda and pip for package management, and create, use, and export YAML files. Before we can understand why we need to use virtual environments, we need to understand libraries first. A library in Python, like NumPy and Matplotlib, that we're going to look at in chapter 8 and 9 of the course, is simply a collection of pre-written code. We can reuse the code that other people have already written for us. There are many libraries available for Python that can enhance the functionality in different directions. NumPy for numeric operations and Matplotlib for plotting, for example. You could use Django to build web applications. Without libraries, Python doesn't have a whole lot of functionality. So without libraries, not too many people would even use Python. With these libraries, you can go in different directions, be it scientific computing, data science, AI, machine learning, web development. And that is the reason we need virtual environments, because you cannot install all these libraries in one and the same environment. Let's have a look at NumPy and Matplotlib, what it can do for us. Import NumPy as NP, then you can use the library functions. And you can, for example, convert a list into a NumPy array with a NumPy.asArray function. Now that our list is converted to a NumPy array, we can use Matplotlib to do a very basic plot of that data. Don't worry, we're going to make a lot nicer plots than this one in chapter 9 and also dive deeper into NumPy and all the functionality that it brings in chapter 8. But for now, all I need you to understand is creating a plot like this would not be possible without using external libraries. Which brings us to the question, why do we need virtual environments? You can think of environments like sandboxes that are completely independent of one another. And you can think of libraries like NumPy and Matplotlib like children. If you have too many children playing in the same sandbox, there are going to be conflicts. So we need to create separate sandboxes for separate projects to keep it civil. In programming, what does that mean? If you install all your libraries in the same virtual environment, sooner or later these libraries are not going to be compatible with one another anymore, and there are going to be conflicts, and then you can't install any additional libraries anymore, which is why the general practice is to keep your virtual environments as small as possible. So only install the libraries that you really need for this project, and if you need more libraries or different libraries for another project, you create a different virtual environment. This might seem complicated in the beginning, especially if you come from other programming languages where you didn't have to do anything like this, but as we're going to see in a minute, creating these environments and activating them is very, very easy. So there's no need to be lazy about creating one environment and installing everything in that one and hope it works. It's just not necessary. You could ask Claude, why are virtual environments important in Python development? Since the answer was quite relevant and I need you to understand this, I copy-pasted the answer in here. So it's basically isolation, so the sandbox stuff, dependency management, collaboration, which means that if I create an environment file, I can give that file to you and you can create exactly the same environment. So this classic problem that you might have encountered already, someone says, well, on my computer it works. On your computer, well, not my problem. This is something you can forego with virtual environments, because if you install the same environment, you can be sure that the same Python script or the same Jupyter notebook will run on both computers. Another reason is testing and development, because if there are some new versions of Matplotlib or NumPy, for example, but you're not sure if they're compatible with other libraries that you have already installed, instead of installing it in the environment that you already have, create a new environment with all the latest versions, test that out, and even if you completely break it, even if nothing works in that one environment, it's isolated. So your other environments will still be intact. What can we use to manage our environments? There are basically two solutions out there. One is Anaconda, so what we installed earlier, and the other one is pip. Pip is a bit older. However, Anaconda has some advantages over Pip, which is why I generally recommend using Anaconda. The main reason is that Anaconda automatically checks for dependencies for your packages and installs necessary additional libraries. So if you, for example, install NumPy in Conda, it will also install OpenMP for parallelization and MKL, the math kernel library, for improved performance when it comes to math operations. When you then do math in NumPy, it can use these additional libraries to speed up performance. I'll link the YouTube video here where they did a benchmark between installing NumPy with Anaconda and installing it with pip, and there was quite a large performance difference. I'll link the cheat sheet here with all the commands for Conda. I'm going to show you the basics here, but this is a really nice reference that has all of them. Pip, however, is still used a lot, so when you Google how to install a package, so how to install NumPy or some other library, you usually get the pip installation command first. However, here you need to be careful because if you mix Conda installation commands with pip installation commands in the same environment, this can lead to unexpected behavior later, because as long as you install all the libraries with Conda, it can check whether these libraries are compatible with one another. And if you do everything with pip, pip can do the same. However, if you mix the installations, they cannot cross-check for compatibility. So then you're just installing the latest version of everything and hope that it works. Sometimes that's okay, sometimes it works, but I've seen this lead to problems many times. So stick to one or the other. If there are libraries that you can only get in pip, you can also create an environment with Conda and then only use pip installation commands if that is necessary. 95% of packages are available with Conda, especially the basic stuff that we do today, but also in the advanced courses, everything is available in Conda. How do we actually install a library now? There are two ways of doing this. You could, in principle, create an empty environment and then install the libraries one by one. So always say conda install JupyterLab, conda install Matplotlib, conda install NumPy. But first of all, this is a bit inefficient in terms of doing everything one by one. And the second reason is, and I've seen this happen, is that when you install libraries one by one, let's say you install JupyterLab, you install Matplotlib, you install NumPy, it will always take the absolute latest versions, because why wouldn't it? But if you then want to install pandas, and pandas and NumPy, they need to be compatible with one another, because pandas uses NumPy in the backend. But if pandas hasn't caught up yet to the latest version of NumPy, then the latest version of NumPy and the latest version of pandas is not compatible with one another. There's a conflict here. But if you tell Conda from the beginning all the libraries that you want to install, then it can check beforehand which version numbers are actually compatible of these libraries, because they are constantly being developed, and only install the ones that fit together. The way to do that is to create these YAML files or YAML files. Once you create it, you can run a conda env-create command to install it. I'm going to cut in from the Jupyter installation video how to do that in practice, because I've already covered it there. Last thing I want to show you here is how to install an environment and how to activate it. Let's say we have an environment file here in our folder. If I want to install that now, I can use this conda env-create command from here, copy that out, open a terminal, and then paste that in here. That will install the environment. Installing an environment sometimes takes 20 seconds, sometimes it takes 15 minutes. It'll depend on how many packages you're installing, your internet connection, how busy the Anaconda servers are. When you want to use it, you can either run this conda activate command if you want to use it here in the terminal. But if you want to use it in one of your notebooks, there's an even easier way. So you can just open that notebook, and then in the top right, you'll see the active environment. And we can switch that now to our test Python course environment, the one that we just installed. You might have to restart JupyterLab in order for this to show up, but then it should be there. You can see in the top right, we're in this test Python course environment. And if you wanted to make that default, you can go to manage Python environments. That opens this window here. You find the Python course environment, you copy the Python path, and in the settings, you make that your default. Whenever you start a new notebook, this will be the environment that is loaded by default. We are back on the Windows computer because there's one difference between macOS and Windows. When you open a terminal here in Windows, it unfortunately doesn't open Anaconda prompt, but Windows PowerShell. And you cannot run conda commands in Windows PowerShell, except if you run through some steps that I show in this video. In this video, I'll show you how to run conda commands in the Windows PowerShell. Two things you need to do: start an Anaconda prompt. Here, run the command conda init PowerShell. And if you get this type of output, it means that it worked. Go back to our PowerShell and run this set execution policy command. I'll put it in the description of the video. After that, restart the terminal, close this one, open another one. You'll see it takes a little bit longer to load, but after it started, the base environment is active. If we run conda, it knows what it means. And if we wanted to install an environment now, copy that out, run that here. It can install it from the terminal from within JupyterLab. So there's no need to run Anaconda prompt again. Make sure that when you install a new environment, you include JupyterLab here in the dependencies, so in the packages that are going to be installed, because otherwise it might not work in JupyterLab Desktop. And we're back. I've added some screenshots here to the script on how to make your environment default. This is something I want you to know how to do because there's no point in installing an environment and then not using it. The lab Python course environment is also in the video description, so you can download it. That covers all the libraries that we need, both for this beginner course and all the advanced courses. In principle, if you only want to follow along with this course, so with NumPy and Matplotlib, there's a base environment. So this one here is the base environment that comes pre-installed when you install Anaconda, and that one usually has NumPy and Matplotlib built in. So if you only want to do today's stuff, you don't need to install a new environment. However, for the advanced courses, you're definitely going to need it. One question I usually get is whether installed environments are available everywhere on the computer or just in the folder that you installed it in. They are available everywhere. So it doesn't matter where you install them from, you can access them anywhere. If you want to create a YAML file by yourself, you can either do that by hand, or you could, for example, ask Claude to give me a machine learning example in Python and the YAML file with the necessary libraries. When we paste that into Claude, we get two things, the Python code here and the YAML file. You do actually get a mixed environment file, so all these are conda installations and this one is a pip installation. We could ask it to get rid of the pip installation if there is a conda replacement. Claude got rid of the pip installation. It's the second version now of the YAML file. What's useful here is that you can now actually download this file by clicking the download to file button here. That will suggest to call it a txt, but we do need the YML ending or the YAML ending. And when you download it to the same folder that your Jupyter is open, it will show up here. So we can open it, have a look at it. Then with the terminal, you can run the installation command. So you go here, copy that out. So you change the file name to the file that you just downloaded, hit enter, and that will install the environment. After installation, you can either activate it here in the terminal, or you can change it up here. However, usually when you just installed it, you do have to restart Jupyter in order for it to show up here. Anaconda Cloud has some pre-installed environments available, but you cannot install any additional libraries to them. So you can use them the way they are, or you need to install your own environment. So when you're on the launcher in Anaconda Cloud, you see that it offers you to start Notebook in different environments, or you can just go to your file and then change your environment here. For what we're doing today, so just NumPy and Matplotlib, all of the available environments here will have that. However, you can also install your own environment for the advanced courses, for example. So you see here, I've done that. And it works exactly the same way as on your desktop. So you upload the YML file, you run the conda installation command, then it'll be available. However, one thing to look out for, even though this environment file isn't particularly large, so this is not a large number of libraries, the disk usage was almost full after installation, so it was about 80% or even more. But if you go to disk usage and you clear the cache, that will delete all the temporary files that were created when you installed the environment, and that will free up some space so that you don't have to pay for a pro account just to have your own environment installed. It's not necessary. So you install it, clear the cache, and you should be fine. One difference that you might have noticed is that in the environment file that I provided, there are no version numbers. However, the environment file that we got from Claude does have version numbers, and there are use cases for both. If you want to make sure that you always get the latest version numbers of all the libraries, at least the ones that are compatible with one another, then go without specifying the version numbers. However, if you do have a set of version numbers that you know it works for, and you also don't need any of the additional stuff of the newer versions of those libraries, then you can specify the version numbers. You don't have to do that by hand, because that would be quite tedious. But you can open a terminal, and for the environment that is active, you write conda env export to some file name. Let's just call it export test.yml. That will create a new file here. And when you open that, you see you get the version numbers, but also a lot more libraries than what we initially had in our lab Python course environment. And the reason for that is in the exported environment, you get all the helper libraries also exported. So when you normally install NumPy, it doesn't just install NumPy, but 6 other libraries, and here you get all of them. So if you give this file to somebody else, you can make 100% sure that you're exactly in 100% the same environment. One last word of advice: once you have a working environment, do not try to update or change it. If you want to change something about it, just create a new environment, do all the latest versions, add some additional libraries to it, and then use that one. The reason for that is I've seen it too many times that you have a working environment, everything works great, you want to install something additional to it, or you want to update your libraries, and then something breaks and then the entire library becomes unusable. Chapter 8, First Steps with NumPy. With all the basic stuff out of the way, we can finally focus on some numerical operations. By the end of this section, you'll understand the basic concepts and benefits of NumPy arrays, create and manipulate NumPy arrays, perform basic mathematical operations, use NumPy's built-in functions for array manipulation and analysis, and recognize the performance benefits of NumPy arrays over Python lists. Let's start with that last point. Why is NumPy so much faster than lists? It boils down to how the memory is being allocated. Whereas in list, if this is your RAM, then one element might be stored here, another element might be stored there, and another element might be stored there. When you loop over an entire array, in memory it has to do these jumps, because one is here, then there's a bunch of other stuff, then another element, then a bunch of other stuff, another element, so on and so forth. Whereas a NumPy array will always be continuous in memory. So if you have 100 values in a NumPy array, then they will all be after one another in the memory. That makes looping over them a lot faster because modern CPUs have vectorization units built in so that they can do one math operation on many array items at the same time. But this only works if they're continuous in memory. Plus, a lot of NumPy functions in the backend are written in C, Fortran, or C++, which are faster languages than Python. So when you call the built-in NumPy functions, they take full advantage of that speed. To use NumPy, simply import NumPy as NP, and NP here is shorthand notation so that when you call a NumPy function like NumPy array, you don't have to write NumPy.array all the time, but NP.array. Most libraries have some kind of shorthand notation that people have agreed on, so when you find code on the internet, it will always be NP.array or NP.asArray. It will never be NumPy.array. It makes sense to use the same naming convention, so when you get code from Stack Overflow, for example, or from one of the AI tools, you can just copy-paste it and it will run. Whereas if you use a different naming convention, you would have to change all the function calls, which is a bit tedious. To initialize our first array, we can call that np.array function. Because it's a function, you have round brackets on the outside. Inside, you basically have a list. When we print that, that is what we get. And compared to a list, you'll see that for the NumPy arrays, when you print them, you don't get any commas, but that's pretty much the only difference in the output. If you wanted to convert your list now to a NumPy array, you can use the asArray function. So you put your test list in here, and then the test list converted will again be a NumPy array. 9 times out of 10, when you want to initialize an array, you already have some range in mind. For that, you can use the NumPy arange function, where you can create an array from the start value, so from -5 until 5 in steps of 0.5. When you print that, you get everything from -5 to 4.5 in steps of 0.5, because also here the last element is exclusive, meaning we create values up until 5, but not including 5. The last value will be the stop value minus the step. The linspace function is same but different. You also have a start value, you also have a stop value, but instead of giving the stepping, you give it the number of values. This will actually create a symmetrical array from -5 to 5, including the 5, which is advantageous if you, for example, want to create a symmetric array around the 0 for a plot, or you want to go exactly from this number until this number, and then you can choose the accuracy by the number of values. Accessing array elements is similar to lists. When you have an array here and you want to print the first array element, you can access array name, so ARR of 0, and that will give you the first element. What you can also do is to access the elements from the back. So if you say array of -1, that will give you the last element, and -2 would be the second last element, and so on and so forth. If you want to loop over your arrays, you can say for x in array, all the individual array elements will be stored in x one by one. First it will be 2, second loop iteration it will be 4, third iteration will be 8, and fourth 16, which is why we get this output. One useful function is enumerate. Let's first have a look at what that does. You get not only the array element, but also the index. You can say for idx, x, so again, like a tuple that we unpack, we can print the index and the value itself. This is quite useful because sometimes you need to know where that array element is. If you do want to search for an element, but you don't want to loop over everything, use the NumPy where function. So NumPy where array is equal to 4. That will give you the index where the array is equal to 4. We see here index 1 is 4, so that's the index we get. As I promised you earlier, all the min-max functions, they're built in Python, and they're a lot faster than what we have for lists. So if we have an array, let's say 16, 8, 32, 1024, 64, and we want to get the minimum, the maximum, the index of the minimum, the index of the maximum, we can use the min-max, argmin, and argmax functions, and then we can print it. To visualize this concept, I created this graphic here. So this is our array. The min function will take the minimum array element, the max function takes the maximum array element, and the argmin and the argmax give you the indices. You have other basic mathematical functions built in. The NumPy.squareRoot function will calculate the square root of the number that you give it. Pi is also saved there as a constant. The exponential function is there, and also an absolute value function. This by far isn't everything that NumPy has to offer. I just wanted to give you some examples here that we're going to use in the next chapter about plotting. We're going to dive a lot deeper in the advanced courses and look at stuff like linear algebra, statistics, Fourier transforms, multidimensional arrays, and then use all that knowledge for some hands-on examples where we do interpolation, fitting, and filtering noise out of large data sets. So if you want to know more about NumPy and you're just not sure yet whether you want to join my courses or not, you can ask the AIs about any of these topics here, and you'll probably get a good answer because the AIs have a pretty good understanding of NumPy. Just to give you an example, we can ask this question here to Claude, start a new chat, and we get the answers: performance, memory efficiency, vectorization, broadcasting, rich functionality. So NumPy provides a wide range of mathematical functions and tools specifically designed for numerical computations. Better for linear algebra, convenient indexing. So NumPy offers advanced indexing techniques, making it easier to access and manipulate data. And also interoperability. So many scientific Python libraries are built on top of NumPy, like for example pandas, making it easy to integrate with other tools. Chapter 9, first steps with Matplotlib. By the end of this section, you'll be able to create plots using Matplotlib, customize their appearance, and generate and understand different types of visualizations. Let's get started. Import our libraries. So import NumPy as NP as before, and import matplotlib.pyplot as PLT. PLT is the standard abbreviation that most people use, so it's easiest if you stick to that. We're going to use the NumPy linspace function that we looked at in the previous chapter to create two X arrays. Both go from 0 to 10, but one has 11 values in between and the other one has 101. Remember the polynomial function that we created in the function chapter? Here I don't define it again, I just put it into a markdown cell so we can see it again. Because a function should be defined in one place and one place only, otherwise you might have different versions of the same function with a different content, and that will lead to confusion in the best case, and worst case scenario, you get some output that is simply wrong. We have it in the markdown cell simply as a reminder. Now we can calculate our y values with this polynomial function with both arrays, x and x fine. To create our first simple plot, we initialize the plot with plt.figure. Then with plt.plot, we plot the first set of x and y values, and then we have another plotting command for the second set of x and y values. We get the fine-grained x and y values as a line, and the coarse-grained x and y values as dots. To customize this and to make it more clear what is what, we can first of all update the RC params to make the font sizes larger. However, if you do it like this, this will update all the font sizes of all the plots in your entire notebook. This might be what you want, but if you want to keep it local, so if you want to keep it only for this plot, we're going to look in the advanced courses how to do that, because there we cover all the topics around making a plot publication ready. Then inside of the plt.figure command, we can specify the fig size to be 6,6, meaning it's going to be a square. In the plotting commands, we can define what marker we want. Instead of the dots, we can use stars, and we can give it a label that will show up in the legend. We can do the same for the second set of x and y values, where the line style is going to be a dashed line instead of a continuous line, and we will call it quasi-continuous. We can create x and y labels with plt.xlabel and plt.ylabel, and inside of the label we can use LaTeX notation to make the formulas look more like formulas. When we execute that cell, we get a dashed line now, we get the blue stars, we get the legend, larger fonts, and x and y labels. Another type of plot are scatter plots. We're going to use Gaussian distributed random values. They will be centered around x equals 3, a standard deviation of 1, and we're going to have 2000 samples. We do the same for the y values. Now we can finally use the dictionaries that we introduced in chapter 2 to collect all the plotting options in one place. Instead of doing it like we did here, with a star, with a label, with the line style, so on and so forth, we put everything first into our random dict. Define the color to be orange, the label to be random values. Additionally, we define a dictionary for the mean value, where the size is going to be 200, color is going to be blue, marker is going to be star, and the label is going to be average. And the advantage of doing that is that now when we create our scatter plot, we use plt.scatter, put our x values in, our y values in, and unpack the dictionary. With 2 stars, you unpack a dictionary. So this will paste everything that's inside of this dictionary in here. There are many options that you can set. Here we only look at a few, but you can in principle set 10 different values, and you don't want to have everything here because again, we're going to hit the line. and it's going to make the code less readable. But this way you have it stored in one place, and you can also change it in one place. So if you make multiple plots with the same style, all you have to do is change it in one location instead of changing it for every single plot, which makes it a lot more flexible. So we scatter plot the mean of the random value in x and y direction and use our mean dictionary. We define x and y limits, so the x and y axis go from -7 to 7. When we execute that, we have the blue star here in the middle and all our random values around it. We can use the same dataset now to plot it in a histogram. This time we use the plt.hist command. Again, with our randomly distributed x values, we define the number of bins and reuse our random dictionary. So when we create that, we get a histogram with the same color as our scatter plot before. If we wanted to change that now, because we say the color that we use here should always be used for the random data. Right now it's orange here and orange there. However, we also had orange here because orange is simply one of the standard colors that Python is going to use if you don't specify it. Instead, we could say gray here, execute these cells again, and this is updated, execute this as well, and now our histogram is also updated. So whenever you see a gray plot, you know it's a random number data set. Two more types of plots that I want to show you here in this quick introduction. First is the contour plot, which looks like this. So if you have three-dimensional data basically, so you have x, y, and you want to color code the third dimension, so the z dimension, you can do that with contour plots. And the way to define them is you create your x values with a range or linspace, the y values, same thing. You create a mesh grid to basically make this entire thing two-dimensional, and then you can use those mesh grid variables, x and y, to generate your z values. If the mesh grid is not clear, don't worry about it. We're going to look at it more in detail in the advanced courses, what this actually does. For now, just accept it as something that you need to use to create this plot. Now that we have the data, we can create the figure. We use the contourf function, give it our x values, y values, and z values, define a color bar, so that's the thing you see here on the right. We set the label of the color bar to be z equals x times y, so that's this one here. And we set our x and y values as before, and to introduce LaTeX notation, we can use the dollar signs. And this is the result. This wouldn't be a plotting tutorial without pie charts, so I created one. To create a chart like this, you define the sizes, the labels, and the colors, and this explode parameter, which basically says that this yellow bit here is exploded out a little bit from the center. Now that we have all the data, we can use the plt.py function, give it the sizes, the explode parameter, the labels, the colors, some formatting options so that you see the 80% here, and a start angle, which basically turns it. We title it Time Spent Programming. What this plot shows us that it doesn't matter whether you're a beginner or not. This is something actually one of my computational physics professors told me at some point. The time you spend programming will be 20% actual programming and 80% debugging. By using the AI tools, you can shift this ratio a little bit. However, if you use them wrong, you'll leave all the actual programming to the AI tools and then spend 100% of your time debugging, which kind of begs the question, who's working for who? So in summary, Matplotlib is a powerful plotting library that can produce professional-looking plots. So a lot of scientists use Matplotlib to create publication-ready plots. And in the advanced courses, we're going to look at inset plots, interactive plots and widgets, creating videos from a series of plots, advanced plotting options, and making your plots publication-ready. If you want to know more right now, you could ask Claude, what are the key components of a Matplotlib figure and what does each do? Or ask ChatGPT, create a Matplotlib plot with multiple y-axes. I'll leave this now to you as an exercise because by now I think you know how to use these tools and I don't want to make this video too long. In Chapter 10, I want to address some frequently asked questions and some common issues I see beginners struggle with because I've been giving Python courses for the last 4 years now and there are some common issues that just keep repeating themselves. So I want to address them here to help you right from the start. First question. Whenever I look at your code, it makes sense, but when I try it, I get errors. Think about learning programming like learning anything else. So think of it like learning a new language or a music instrument. It's one thing to watch somebody play and say he or she plays well. It's another thing entirely to be able to play well yourself. A few tips you can use as a beginner, but also something I still adhere to as an experienced programmer. First of all, keep the code cells small. It's much easier to find a bug if there's 3 lines of code than to try to find the needle in the haystack. With that in mind, work your way forward in as small steps as possible. So write a line of code, execute it. Write another line of code, execute it. So if you get an error, you immediately know where it's coming from. Instead of writing 100 lines of code, executing, and then you have 20 errors in there, and you spend 2 hours just debugging. That gets frustrating pretty quickly. Third tip is learn how to read error messages. So remember, the important stuff is always at the bottom. All the rest just tells you which line of code created the error. and you can actually go back to the function section, error messages, where we covered the error messages more in detail. So all the different types of errors and what they mean and what to look out for to fix them. And also here, learn how to use the AI tools. So either copy paste everything into ChatGPT or Claude, or develop right from the get-go in Anaconda Cloud and then use Anaconda Assistant to help you debug that code. Second question, how to think like a programmer. So often I get the comment, okay, I understand all the tools, but now if I want to solve a problem, I don't even know how to get started. So in this video, I showed you some tools to get started. So imagine you're a handyman and you just learned how to use a screwdriver, a hammer, and a saw. Instead of saying, okay, now I'm an expert and now I'm going to build a house, maybe start with a small bird's house first, and then build a dog house, then a garage, and then build a house. Like with everything else, it comes with experience. A few tips here. Programmers usually have a divide and conquer approach to solving problems. So instead of trying to solve the entire problem all at once, you break it down into as small parts as possible, and then you solve them one by one. You climb a mountain one step at a time. You don't try to jump from the bottom of the mountain right to the top. AI tools might help you get there faster, so they're basically your Sherpas in climbing the mountain, but they might also lead you on the wrong path. To give you a divide and conquer example, usually with scientific applications, in the beginning you want to read in some data that comes from an experiment or a simulation, so file I/O. After you've done that, you need to process that data that you've read in. And after the processing is done, you want to visualize it. You want to create a plot that you can put in your thesis or your paper. So that's already 3 large steps. Now we can break all of these steps into smaller sub-steps. File I/O, for example. The first sub-step is what format is the data in that I want to read in. Second step is how do I read that data in? Third step might be in what kind of data structure do I want to store that data in Python? So is it going to be a NumPy array, a pandas data frame, a dictionary, a list? Make a decision there. Then you actually read in the data. And ideally, you also have a check in place to make sure that the data was read in correctly. In terms of the sub-steps of data analysis, sometimes it makes sense to actually work your way backward. So you think, what do I want my result to look like? And then work all the way back to the data that you have. Second step, decide for the method of data processing. So how do you get from here to here? It might be an interpolation, a fit, a filter, whatever it needs to be. Then you actually do the processing, and then you make sure that the result makes sense. But with visualization, it also makes sense to work your way backwards. So first have an idea of what the plot is supposed to look like in the end. So is it going to be a histogram or a scatter plot or a contour plot? You should choose something that best represents the point you're trying to make. So don't just throw data in a plot and hope it looks good, but think, what argument are you trying to make with your data? Choose a plot that fits that. Then you actually make the plot with the final results from your data analysis. And in the last step, you make that plot publication ready. So you change the fonts, you change the styles, you add a legend, all that kind of stuff. Another tip here is learn from other people. To go back to our handyman metaphor, if you watch some do-it-yourself home improvement videos, you might get an idea how other people solve the type of problem that you have. To come back to Python, I will create videos in the future where I take a problem, break it down step by step, and then solve it and show you all the steps along the way instead of just showing you the final result. So also from there, you might be able to learn. So subscribe to be notified when those videos come out. Third issue, I wasn't sure how to highlight it, so I used 3 red crosses and 3 skulls to make absolutely sure you get this point. Do not name your variables and functions after built-in keywords and built-in functions. We saw it all throughout the script. If there's something like this, if this turns green, then it's a reserved keyword, so do not use it. Yeah, absolutely 100% never ever do this, all right? And just to give you a reference point here, what are all the built-in keywords and the built-in functions? Those are all the keywords here in this table. And in the next table, you have all the functions. Feel free to use these functions, but don't overwrite them. Next, which one of the AI tools should I be using? If you don't want to spend any money, I would just use all 3 and take advantage of the free usage per day limits, because all 3 of them have some limits. But if you have all of them, you can just use the limits of one, then use the limits of another one, use the limits of the third one. And you're probably not going to need more most of the time. However, if you want to go with one, it depends a little bit on what it is that you want to be doing. Anaconda Cloud is great for in-place debugging. So if you want to have this Anaconda Cloud feature with Anaconda Assistant on the right where you can code and have the assistant basically watching your code, it's quite useful for that. Plus on Anaconda Cloud, if you do pay, you also get more storage space so you can create more virtual environments there. However, Anaconda Cloud is basically only for programming. So if you want something that is more general, I would either go with Claude or ChatGPT. Right now I prefer Claude because of the artifacts and also because of the comparison that I made between Claude and ChatGPT 4.0, where Claude 3.5 Sonnet was better. However, ChatGPT just this week released ChatGPT 0.1, which apparently now is better, but I haven't tested that yet. So just try it out. They're both pretty good for both programming and for general purpose stuff. Next question, what are some common Python libraries for data analysis and when should I use them? The main ones are NumPy, Pandas, Matplotlib, and SciPy. NumPy and Matplotlib we cover today, at least the basics. Pandas and SciPy we do cover in the advanced courses, so Python Basics, Python for Scientists and Engineers, and Python for Biologists. So if you're interested to join the courses, either as an on-demand course, so where you have video lectures like this one, or a blended learning course where you additionally also have Zoom meetings where you can ask me questions directly, you can sign up for them on trainingscientists.com. Question 9, how can I collaborate on Python projects with others using version control? Out of all the version control software, Git has won the version control war, so pretty much everybody is using it at this point. There are different servers available, so most people are using GitHub. However, GitHub is run by Microsoft and they are using your code to train their AI models, so ChatGPT basically. So it's up to personal preference now if you want to do that or not. There's GitLab, which is open source. You can host that on your own server if you have one. There's also Bitbucket as an alternative. And also this we set up in the advanced courses and applied with some practical examples. Last question, now that I've watched the video, how can I improve my skills further? So first, and I have to say this because I do want this course to be free, but I also gotta eat. You can get the exercises that are tailored to what you've learned in this course on trainingscientists.com. To get a 50% discount, simply leave a like and a comment under the video and contact me on LinkedIn and I'll send you a voucher code. If you don't want to do that just yet, just take this notebook, create a duplicate. When you go to the File Explorer here, you can do a right click and then duplicate this notebook. And in the duplicate version, you can just play around with it, intentionally break things, check out the error messages, change some things around, and get some experience that way. Either way, my recommendation is always after you've watched a video, put into practice what you've learned. Don't just watch video after video after video and never actually get to doing anything yourself. Because again, if you watch someone play the piano 100 hours, but don't ever play yourself, how good are you really going to get? Ideally, try to solve some small problems that are relevant to you and start coding. You can use the AI tools, but always try to understand what you're copy pasting. This will help you actually learn instead of now just having a foundation and letting AI do all the complicated stuff. Because again, AIs will make mistakes, and if you don't understand what they're doing, you cannot fix them. Which is why in the advanced courses, we always have a video lecture, but then also exercises to put what you learned into practice, and then Zoom meetings in the blended learning courses where we can discuss the exercises, you can ask me questions directly, and we can discuss topics that go beyond the courses. And another thing you could try is to ask ChatGPT to suggest some small Python projects for beginners to practice their skills and work from there. If you've made it all the way to the end of the video, thank you so much for watching and see you in the next one.